Hi guys, today I'd like to finally start to talk about a little bit about physics. I will start with some simple example. Uh, I don't, not so for sure. I'm not very sure if it's interesting at all, but it's just a way to break the ice, and then maybe we can at some point talk about something more interesting. But let's start from something easy that I can handle. So, okay. So, what do we want to talk about? Yes. So let's think about um, a falling object. So suppose you are here and then you hold in your hand a bowl or a stone. Okay, so whatever it is, what matter? And the first thing that we need to remember is that we want to, for example, fix frame of reference. Okay, so since we usually with physics and math you want to get numbers to things, objects that are moving or things that are changing, then it's good to start with some rurals. So so we are in 2D at the moment. So we just think about x and y. So up and down and left and right. So we don't think about the depth of our situation. And to do that, we introduce two vectors. We know what vectors are, so we can do it. So we introduce one vertical vector, which starts from this point here, and then a horizontal vector. Okay, so those two vectors are just guiding directions in order to uh, give us, as I said, two lines, basically the direction of two lines, which are basically thought as real numbers in this case. So we can think about this line as chopped into many pieces, which are in this case, the length expressed in real numbers. Okay, so you can think about this as real number, and the vector are just directions. Okay, the vector I'm talking about is v0 and v1, or actually vx and vy. Let's call them like so. And this is 1 0 and 0 1. So these are just to give us a direction. But what we care about is that any point in this, and we call, by the way, we call this a special point that I draw in red. We call it 0 0, or the origin. Okay, so this is the origin of our frame of reference. Frame of reference meaning that we now can, if we pick any point, let's call it P, we can associate to this point two values, xp, chopping his head, and yp. Okay, and xp is equal to xp and yp, and we know that two numbers can be represented as a vector as well. Okay, so I don't want to overcomplicate this, but I'm just saying that you can write this number p, you can associate to this number p, so each point a coordinate pair of coordinates, which is a vector. Indeed, it's a vector. Okay, now what I want to say, okay, just to let you know, these two vx and vy are two vectors, special because we can write any other vector p in terms of any other vector, any other point, in terms of vx times whatever a number is, plus vy, change the color, b. In this case, it's very easy to prove this fact, because vx we know that is 1 0, vy is 0 1, we want to have x and p, so a will be xp and b will be yp. If we do this, the sum and the multiplication of the vector with the number, we know how to do that because we saw it, but we can refresh it and we get xp, which is indeed our vector p. Okay, so this is just to give you an idea that you can play a little bit with vectors and coordinates in this way. Not going too deep in this direction, but we'll see that. So just want to say that changing the reference of frame can be very helpful in many situations because it will help us to reduce the number of coordinates that we need to solve the problem, or it'll help us to rewrite the problem with math that is easier to the component. We will get that to the natural when we do other example. For this one, let's pick the most intuitive one. Maybe it's not the best, the most convenient, but let's stick with this origin there and let's see where it goes. Okay, so we have a point P, then now we can forget about it, and then we know that we have a ruler in x and y, so we can locate our position. Okay, now let's make some assumptions. So, well, there are many assumptions here. So the first one is, let's say there is no air. So our man here must wear a mask and some oxygen, O2 supply. Okay, so okay, because there is no air, he cannot breathe, but we make him breathe with some equipment. Okay, so nice. So the other, so there is no air because I don't want to deal with friction. Okay, so no air means no friction. Okay, it makes my life much easier. Friction is not easy to incorporate. It requires a bit more, well, quite a bit more of math and physics and assumption and stuff. But the thing that is interesting to remember is that friction it's super important for aerodynamic, if you think about it. So any falling object will be affected by friction in one way or another. If you think about a football match when the ball is curving, or if you think about a leaf that is falling from a tree when it's autumn or whatever. If you think about aircraft, F1 machine, car, whatever. I mean, even missiles. I mean, I'm not saying that. So air is definitely important, but let's forget about air and let's stick to something very easy to start with. The other assumption is that we will think. So this is so you can think that this object here is actually a stone, but a stone usually have many shapes, can have many shapes, whatever. It can be a brick, it can be a log, it can be anything, any shape you want, okay? But I'm a physicist, so I don't like to complicate my life if it's not necessary. So let's circle all of this in one single point. Okay, so it's a point where there is no geometrical structures, meaning that we are simplifying a lot the rotations, okay, because a point does not rotate while a brick can rotate, and the symmetry of the problem are way much reduced. In fact, there is no, well, point has, I don't know how many, but basically so if you think about a stick that is falling, it can actually rotate around the central point, or it can rotate this way, it can rotate otherwise. A point just fall and doesn't matter. You can think about a sphere if you like, if you don't like points. Sphere is a good approximation. A sphere technically can rotate and can feel the drag of the air. In fact, if you think about any ball in a sport, will feel the drag of the air. So just to make sure that we are not dealing with those as well, which maybe we'll do in another video later on, but let's even forget about sphere. It's literally a point, okay? It's an oversimplification, but it can help. Okay, so we have a point. What else do we need? So we said that we have our reference of frame, we have no air, we have our oxygen supply, so we can do the experiment. What do we need? Oh yeah, sorry, we need a ground. So we need a ground, and therefore we need a ground, and therefore we need a planet where to live on. So let's suppose that this is Earth. Oh, actually, it could be Mars. There is no air on Mars. But okay, so it doesn't matter. What I want to say is that we need ground because we want to have a big mass that will attract our small mass m. So, okay. Now, you see where I want to go, right? So, to make an object move, Newton's laws tells us that we need a force that acts upon the object, and the force induces or is equivalent to an acceleration times the mass of the object. Okay? Now that means an acceleration, we know what, so now we can forget about the arrows. No, we can keep the arrows, but let's keep the arrow just to remember that are vectors. But what I want to say is that an acceleration is, we know what it is, it's a derivative. Okay, we didn't see technically what's a derivative of a vector, but it's very easy because you can differentiate the velocity, and it's a vector, so you can differentiate the coordinate x of the velocity and the coordinate y of the velocity in this case with respect to time. So at the moment I'm not going to refresh what the derivative is. We know what it is. It's a vector derivative, so there are two components, each of them is a derivative. Also, we know that derivative is, velocity is the derivative of space. So if you think about meter per second, right? So when you drive your car or your scooter or whatever, you go at miles per hour, kilometer per hour. So meter per second, meter over second, as you see, it's a derivative of space over time. And then acceleration is another derivative. So technically it's a second derivative with respect to time, 2 times of x, and the derivative of 2 times of dx twice in y. Okay, we know how to take derivative twice because we take derivative once, so we do it twice. Okay, so we know what an acceleration is. Now, I'm not going to discuss what the mass is. Let's think about the mass as whatever react to the gravitational field. So basically, it's a property of any object that reflect the fact that they are composed by many particles. Many particles has an elementary mass associated with it, and then you basically grow this quantity depending on how many components you have in your system. Okay, it's related to the weight, of course, because mass and weight are related by an acceleration. In fact, the weight is a force, and the mass is the constant of proportionality between an acceleration and the mass itself. But let's not go deep. So you think about the mass as a weight is not a big deal because on Earth the acceleration is basically constant anywhere. So we are happy with this, and we know that the force induces a movement, an acceleration, so a change of position. Now, what else do we need before we carry on? Yes, the acceleration. No, actually the force. We need the force. Which force is acting upon this? There are actually two forces that are acting at the moment. One is the fact there is a big mass below the ground, which is the Earth mass, that is pulling the small mass towards the center of gravity. exactly. And let's call this arrow, red arrow down, and this is a force that is, we know what it is. Let's call it F big G. I will tell you in a sec what it is. But then we know that since the man with the oxygen mask is holding the mass is not moving at the moment. So there must be another force that counteracts the force of gravity, and this is the force that is given by the hand. So it's the fact that the stone is, your muscle basically keeps the stone in place. Okay, this is the initial condition. Okay, so let me break the video down here a second, and then I'll be back for the second part where we say why we need the initial condition and how we see what's happening when we do something with this initial condition that changes the state of motion of the object, and then we will see how to simply derive an equation and maybe put some numbers to get an idea of what's happening. Okay, let's stop here and see you soon.